Hello and welcome to the second video of section 2.9 on differentials. In this video, we use linear approximations to estimate function change. Take 2 points p and q on a function. Moving horizontally from p until directly below q, and then moving vertically to q, a right triangle can be constructed. The base has length delta x, which is the difference in x values between p and q, while the side has length delta y, the difference in the y values. The hypotenuse is a segment of the secant line. The amount of function changes between p and q is delta y, or f of b minus f of a. In the first video of this section, we use linear approximations to estimate values. Given an x value a, the linearization of f at a is the line L sub a. For values near a, say b, the actual value f of b is approximated by the line L sub a at b. We can construct a right triangle with side length delta y, the actual change in the y values between x equals a and x equals b. And we can also find in this side length the measurement dy, the height defined by the tangent line L sub a. Delta y is the actual change, f of b minus f of a, while dy is the estimated change, the differential, which makes use of the tangent line. Since dy is the change between the value f of a and the linearization of f at a, we can use the formula from the linearization of f at a to rewrite dy as f prime of a, b minus a. Notice that b minus a is the change in x values. We have been denoting this delta x. Therefore, the formula for the differential dy is f prime of a delta x. The differential notation should remind you of Leibniz notation. This is the intent of the notation. Be very careful not to view dy dx as a fraction. Dy dx represents the instantaneous rate of change for y with respect to x. When taken separately, dy is the change in the tangent line for a given change in x. The notation is cleverly chosen to feel intuitive. Imagining dy dx as a fraction will help you remember the differential formula, but that is as far as it resembles a fraction. Why are we interested in the value dy? As we saw in the previous video, as b gets closer to a, L sub a of b, the linearization of f at a, is approximating the actual value f of b. In this way, the differential dy will allow us to estimate the actual change delta y. For example, suppose an object is roughly spherical and you are able to measure the radius. You take a ruler and measure the radius as 10 centimeters. Using the formula for the volume of a sphere, we can calculate the volume at 10 centimeters. Suppose the precision of your measuring device was 1 millimeter, or 0.1 centimeters. That is, you were using a standard ruler whose smallest measurement is a millimeter. Even though we measured the radius as 10 centimeters with the ruler, the actual radius could be between 9.9 and 10.1 centimeters, or delta r equals plus or minus 0.1 centimeters. We can use the differential dv to calculate the range for the difference the actual volume is from the volume at 10 centimeters. We take the derivative of v with respect to r, we replace r with 10, and delta r is the same as dr, and we obtain dv is plus or minus 40 pi centimeters cubed. To put that into perspective, the volume is measured at 4,189 cubic centimeters, but can be off by as much as 125 cubic centimeters due to the precision of the measurement.